Sure. Here is a full-length, beginner-friendly presentation script on self-supervised representation learning using contrastive predictive coding in sequential multimodal sensor streams, perfect for a 6 to 10 minute talk. Imagine you're in a crowded airport, with conversations buzzing in different languages, people moving in intersecting directions, and boarding announcements echoing overhead. Despite this apparent chaos, your brain seamlessly stitches sights and sounds into meaningful patterns. You somehow know where to look, which voice to pay attention to, and when to move to your gate. This astonishing ability to make sense out of streams of information, coming from multiple senses at once, is a remarkable product of millions of years of evolution. When it comes to artificial intelligence, though, teaching computers to understand and combine information like humans do is a huge challenge. And that, in essence, is the heart of today's topic: self-supervised representation learning using contrastive predictive coding in sequential multimodal sensor streams. Don't worry if that sounds intimidating. My goal today is to unpack what that means, why it matters, and how it's shaping the future of smart systems. Let's start with the basics. In simple terms, the problem is about helping computers automatically create useful summaries or representations from a flood of sensor data. Think of cameras, microphones, or even weather sensors, all of which produce different kinds of information over time. Traditionally, teaching AI systems to understand such complex data required a lot of labeled examples, such as thousands of tagged images or hours of annotated audio. But isn't it a bit like learning a new sport, only if a coach reminds you what each movement means? What if, like human babies, computers could learn patterns and connections directly from raw experience, even before anyone tells them exactly what's going on? That's where self-supervised learning comes in. Self-supervised learning is a branch of AI where systems learn by creating their own training labels, cleverly using the structure within the data itself. It's akin to solving a puzzle where some pieces are deliberately hidden, and you have to guess what fits based on the surrounding clues. This not only requires no external annotations but pushes the AI to look for what's common, predictable, and meaningful across the data, just as we do. Now, how does this work with contrastive predictive coding, especially in streams of multimodal, sequential data? Imagine you're listening to music while also watching a dance performance. Both the music, audio stream, and the dancer's movements, video stream, are sequences. They evolve over time, and importantly, they're connected. Contrastive predictive coding, or CPC for short, is an approach where the computer tries to predict future parts of one stream given its current and past data, and often, additionally, using other related streams. The contrastive part means the AI is constantly comparing what it thinks is the right future with many wrong alternatives, learning to tell good predictions from bad ones. Let's use another analogy. Suppose you have a friend who's learning to forecast the next move in a chess game, given the previous positions. The friend gets better over time if, each time, they're not only shown the real next move but also a random move from a different game, and asked which is correct. This sharpens their sense of the underlying logic. Similarly, CPC trains neural networks to tell whether a snippet of, say, audio really follows a video sequence or if it's a mismatched chunk, thereby learning powerful abstract features, or representations, that capture the essential structure of the data. But why multimodal and sequential streams? Many real-world scenarios are inherently like this. Take a self-driving car. It must process video from cameras, signals from radar and LiDAR sensors, and possibly audio alerts, each providing a unique but related slice of reality, and all unfolding over time. Getting the computer to learn rich representations from such coordinated sequences, without explicit supervision, means it can become much more flexible, robust, and aware, even in new situations it hasn't been specifically trained for. So, where does this show up in practice? Let's look at a few examples. First, consider automated video surveillance in a smart city. Instead of labeling endless hours of security footage, a system can use CPC on synchronized video feeds and ambient audio to learn what normal looks and sounds like over time. It gets good at predicting which audio and visual events typically go together, for instance, the sound of footsteps matching people walking. When something unexpected happens, a loud bang without anyone in the frame, it can flag this as unusual, even if it has never seen that exact situation before. Second, think about health monitoring. Wearable devices capture heart rates, movement patterns, and even voice or breathing sounds, each as ongoing streams. By training a model to understand the relationships among these signals over time, CPC-based self-supervised learning allows detection of subtle deviations that might indicate fatigue, stress, or oncoming illness, without requiring thousands of labeled medical events. A third scenario: autonomous robots operating in a warehouse. They must marry visual navigation cues with touch and force sensors to manipulate objects safely. By learning to predict the next camera frame or tactile reading based on previous ones, the robot can develop an intuitive feel for its environment, making it safer and more adaptable, even in unpredictable conditions. Why does this matter? The combination of self-supervised learning, contrastive predictive coding, and multimodal sensor data holds immense promise for building AI systems that can make sense of complex, messy, real-world situations with much less supervision from humans. It means smarter assistants, more adaptive robots, safer autonomous vehicles, and even breakthroughs in fields like healthcare and environmental monitoring, where labeled data is scarce but streams of sensor data are plentiful. You might be wondering, does this technique replace human engineers or experts? The answer is, not entirely. While it reduces our reliance on labor-intensive manual labeling, humans are still needed to design the goals of the system, ensure ethical operation, and interpret the AI's findings. Think of it more as giving computers better intuition, rather than absolving us of responsibility or expertise. Another question you might have is this how conversational AIs like ChatGPT are trained? Partly, yes. Techniques inspired by self-supervised and contrastive learning are used in natural language models to learn from text without explicit labels. But when dealing with streams of multimodal and sequential data, such